Hi, I'm Cullen. Welcome to Networking Fundamentals. This is Mod 1. We're going to focus on understanding local area networks. Thanks for joining me. Really excited to teach you about networking. Let's get started. Quick overview of our agenda. We're going to discuss local area networks, talk about data transfer on a local area network, also known as a LAN. And we're also going to feature the different types of local area networks that you might come across. All right, local area networks. So first, what is a network, right? A network is just two devices that are connected to each other with a physical medium, like a wire cable or a radio signal. This picture here, just a wired cable, like an Ethernet cable. The connection allows two devices to just exchange data back and forth. So there we have some data moving across, some binary there. We'll talk about binary in a little bit. Networks have a lot of different purposes too, okay? They're used for communication and collaboration inside of a business or an organization. They allow us to share information and resources like text and tweets. They make it possible for us to organize data. They also allow us to save a lot of costs because we can share resources like printers and other different services that are available through networks. All right, so how are networks organized, right? Like we have all these devices around the world. How are they organized with one another? Not just around the world, but also inside of the same building. They're organized based on their geographic location or where they are in the world, in a building or in a city. A local area network or a LAN is simply a group of computers or devices that are featured in the same small geographic location, right? So like a school or a small office. They all share a common communication medium. So, you have cables like we talked about earlier, or also wireless connections. They're also connected to something called a central connecting device, which we'll detail here in a little bit. Those can be hubs, switches, or routers. All devices that are very important to learn about. Network documentation, I guess. If you're designing a network, you have to define and describe and explain how different devices on a network are connected, right? We want to know the physical location of each of the devices and also how they're connected logically, like the general design, right, that we have up in our brains. The documentation phase occurs before you actually build networks or whenever you make changes to a network. And I just want to highlight Microsoft Visio as a tool that can be used in order to design networks on your PC or on your laptop. All right, so what devices make up LANs? We've got hosts, right? Your phones, laptops, desktop PCs, servers, and tablets. We also have central connecting devices, which are hubs, switches, and routers. We typically interact as users with host machines. Those host machines then connect to central connecting devices, which are responsible for relaying our data to other host machines. Hosts, we already detailed the different types that are available, right? The different kinds that there are. But a host is defined as any device that has something called an IP address. An IP address is used to send and receive information. It's very similar to your mailing address for your house. Pretty good way to remember what an IP address is and what its function is. And IP addresses help identify not only the device, so like your house, right, but also the networks where they're located. And if we go back to that home address analogy, a network would be sort of like your city or maybe even your street block. Central connecting devices, as I mentioned previously, are for connecting hosts and also transmitting data. Different central connecting devices, they perform these functions in different ways. And I'm going to show you, model for you those different ways here in just a second. Okay. First, we'll get started by talking about hubs. Hosts send data to a hub, and then a hub then broadcast that data to any other device that's connected to it. This is sort of an antiquated technology. It's old and becoming more and more obsolete, if it isn't entirely obsolete already in most parts of the world. But what happens is it is going so this computer, this device, like you just saw in the demonstration, sends its data, and then every other device that's connected to a hub is going to receive that data. The difference, though, or rather a potential problem here for us, is that this computer may only want to send data to this laptop down at the bottom of the screen and not to the server that's located up at the top right. We're able to correct this problem with devices called switches. And unlike hubs, switches send and receive data simultaneously, and they also send it directly to its intended destination. So take a look at this example here on the right. Okay, so you've got data being sent simultaneously, not even necessarily between two different devices, but amongst different devices entirely, and they go specifically to their intended target. So you saw the yellow piece of data there go from the PC to the laptop, and you saw the turquoise or green piece of data there go from the laptop to the server. Okay, and switches, I guess a good way to summarize it is switches are just simply smarter than hubs. Let's talk about routers. Routers are at the edge of a local area network, and they're the devices that are responsible for connecting us to the internet. Okay, they act as a gateway to other networks. Okay, routers allow communication between hosts on different local area networks. So we can actually connect to local area networks via a router, and that's actually how you make up the internet, right? You connect a bunch of local area networks to each other. Here's a quick example of that data going out to the internet. Pretty cool stuff, right? All of these devices connect to each other via network adapters, right? Network adapters are also known as network interface cards, and these are the pieces of equipment that make it possible for computers and even our cell phones to communicate with each other, right? NICs communicate via wires or wireless signals, and this guy right here, this wired adapter, it features something called an RJ45 port. Wireless adapters feature an antenna in contrast, and they connect to networks using wireless access points, which are, they're also an essential connecting device, and we'll detail them a little bit later in a different module. And of course, if we go take a look at our RJ45 port, we have to have something that we can connect that to or connect that with. And what that is an Ethernet cable, right? Ethernet cables are made of copper wires. They transmit data in the form of electrical pulses. Okay, wireless communications, they rely entirely different technologies, radio signals. Okay, so keep in mind that copper cables transmit data in the form of electrical pulses. You may have heard me mention binary data earlier, and electrical pulses, if there's a pulse, it might represent a state called on, and if there is, so let me write pulse here real fast, and if there is no pulse, then that represents a state called off, all right? We normally say a pulse would be like 1, on would be represented by a 1, and then no pulse would be represented by a 0. And that is called binary. I apologize once again for my atrocious handwriting. So here we will talk about wireless access points just a little bit. They provide a central point of access for laptops and cell phones and even PCs and households, right? We can wirelessly transmit data to these wireless access points, which are actually connected to switches and to routers, right? So even though we access a network wirelessly, that data still is transmitted across a wired network, which I think is something that's super interesting. I'll just point out that little wire there. All right, so now let's switch modes and talk about data transfer on LANs. Data is transferred through serial data. Sorry, data is transferred in a serial format. So that means 1 bit of data at a time is sent. Now, data can travel in a single bit stream in both directions, like to and from. And how it does that depends on the type of connection. And you've got a couple of different types of connection. There's something called simplex, which is like a one-way street. So data can only transfer from one device to another. Whereas we also have something called duplex, which is like a two-way street, which means that the data can be sent and received at the same time. There's also another format called half duplex, which means that you have two streets, but only one of them is in use at any given point in time. Okay, so data can only be sent to and then also sent from, but not at the same time. Okay, all right, move on to the next slide here. The speed that data travels is measured by bits per second, right? That's called its data transfer rate. So we signify this data transfer rate as in, we've got the number there, so 10, right? And then M, which in this case stands for mega, right? And then we have a lowercase b. This lowercase b is a little bit different from the type of data that we store. It represents bits, right? Not to be confused with a capital B, which would represent bytes. This whole construct down here, right, is called the bit rate. And we use that to measure how fast data transfers over a network. So before data is transferred, it actually goes through this really interesting process, right? We break large chunks of data into things called segments, okay? Addressing information is then wrapped around that segment, and we call it a packet. From there, we then add a little bit more information in order to make it something called a frame. And then each frame is broken into the bits that we see on the screen. This visual might be a little confusing, but just know that really data is ultimately going to be represented in bits before it's transmitted across a network. So this whole thing ends up taking this form right here. And then it's transferred over a physical medium in binary. All right, and of course, when data is received by a device like your cell phone, it goes through the reverse process. So what happens is that the receiving computer is going to go ahead and take all those bits. It's going to read the frame, or rather it's going to reassemble the Ethernet frame. It's going to strip that physical addressing information, and then it's going to strip the logical addressing information known as the IP address. So it's no longer a packet anymore. It's going to come back into its segment form, and then it's going to be reassembled into the file that we click on in Windows Explorer, which I think is a pretty cool process, and it actually really simplifies the way that data transfer occurs. All right, so how does data know where to go? Well, we mentioned IP addresses, right? Those are logical addresses that uniquely identify a device and its network. So an example here would be 192.168.1.1. Every IP address is broken down into two different parts by something called a subnet mask, which we'll detail here in a little bit. And so we have a network ID portion, which is 192.168.1, and then the host ID, which is 1. This network ID, think of it as like city and state, I guess maybe your street name. And then we also have the host ID, which would be like your house number, right? All right. Another thing that's really worth mentioning is that IP addresses, the way that they appear, note these little dots that split up the different numbers. Those separate octets. We'll detail IP addresses a little bit more later, but octets actually are just 8 bits. And there are 4 octets in an IP address, which means that an IP address is 32 bits, so 32 zeros and ones. Like I just said, we're going to go ahead and touch on the subnet mask now and detail that a little bit more. A subnet mask is just a group of 4 numbers that define a computer's network. All right, so if you look down here, 255s represent the network portion of an address. So 192, 168, and 1, just like in the example that we just saw. Okay, and then a 0 is going to represent the host portion. So if I change my slide color, or sorry, my pen color here, this 4th octet is the host portion, right? So that's like our street address. In contrast, over here, everything that is represented by a 255 is going to be our network portion. This is really important for us to keep in mind as we're learning this. We'll revisit it throughout this course. All right, so finally our last little objective for the day, types of local area networks. Wired LANs come in different forms, right? And we have these wired LANs where each PC is connected to a central connecting device, whether it's a router or a switch, via an Ethernet cable, right? A copper-based twisted pair cable, in fact. We also have our wireless LANs, where each of our devices are going to connect to a network via Wi-Fi signals, right? Radio signals that transmit data ultimately onto a wired network. And finally, we also have a very special type of LAN called a virtual LAN. Virtual LANs can be wired or wireless. In this example, they're all wired, right? And VLANs allow us to group devices based on their functions. So in this example to the right, we've organized our computers on our network based on teachers and students. So I've tagged any data that comes from the VLAN 30 teacher computers with just a little bit of information, a little bit of data that says, hey, these computers can communicate with each other as if they are on the same physical network. If VLAN 20 tries to communicate directly with VLAN 30, if those devices try to communicate with their counterpart devices, then it's going to be treated as if they're on a separate network entirely, right? So do keep that in mind. We'll detail VLANs a little bit more later on in the course, but super important to keep in mind, right? Also, physical location of these devices doesn't matter at all. Where they're located, these two, you could have two devices sitting right next to each other, but they can be treated as though they're on completely different local area networks. It's a really cool technology and something that definitely makes it a lot easier for you to manage a network and potentially even keep some devices more secure than others or provide different sets of rights to devices based on their organization affinity. All right, so thanks so much for joining me here. We'll just do a quick recap of our agenda again. Covered objective 1.2, understand local area networks. We talked about what local area networks are, just data transfer in general on a LAN, how data gets from one place to another, and also the different types of local area networks. I'm really excited to continue our journey through networking fundamentals again, so I'll see you in just a second in Module 2. Hi, I'm Cullen. Welcome back to Networking Fundamentals. Today we're going to cover Module 2 of Understanding Local Area Networks. Let's go ahead and review our agenda and get started. So we're going to cover Objective 1.5, Understand Network Topologies and Access Methods. In doing that, we're going to review what network topologies are, talk about Ethernet standards. These are standards that govern Ethernet communications. And also talk about peer-to-peer versus client-server models. We'll detail both of those models in contrast to one another. All right, let's move forward. Network topologies. A network topology just defines the physical connections of hosts in a network. And there are multiple types of these topologies, right? We've got bus, star, ring, and mesh. I'm going to go ahead and show you each of those right now and talk about how they function. All devices in a bus topology are just connected via copper cable and a line. So if we have a computer up on the left here, computer 1, if it wants to send data all the way down to computer, let's go 1, 2, 3, 4, 5 computers, right? So I have 5. It has to send data through computer 2, through computer 3, through 4, and then 5, and vice versa, right? So not the most efficient way to send data. Next, we also have a star topology. It's an advancement over the bus. Each host is connected to a central connecting device, like a hub or a switch or a home router, right? A SOHO router. It stands for Small Office Home Office. And this is the most commonly used topology that you're going to find in an office setting, a school setting, or even at home. Note, though, that you can actually connect two of these star topologies to each other via central connecting devices. And this type of topology is called a star bus topology. So we would connect the central connecting device to another one here that would then connect to computers elsewhere, right? And I'll just central connecting device. All right. Let's talk about Ethernet standards. So we connect all these computers to each other, all these devices to each other via copper cabling, and there are standards that govern this process. Ethernet simply is that standard, right? It defines how data is sent and received between devices. And it's the most widely used standard on the internet, so it's very ubiquitous. It's used all over the globe. There are a couple of other standards that are used, though. You've got token ring, which each device actually has to have or possess a piece of data called a token in order to be able to send data on a topology. Then you also have FDDI, which is a topology used for fiber optic communication. This Ethernet standard is governed by the Institute of Electrical and Electronics Engineers, IEEE, and it's referred to as 802.3. Devices that use the Ethernet standard transmit frames, and we had mentioned the word frames earlier, but a frame is just a sequence of bits containing a detectable beginning and end. And so here, this is a little cartoonish, and I apologize for that, but I thought it'd be funny if I actually put a frame up on the screen. Frames contain physical address information that helps switches determine where to send data. So switches don't actually send data using IP addresses. Switches send data, or they navigate data by using MAC addresses or physical addresses. We'll talk about what a MAC address here is in just a second. All right, let's talk about the client-server model here, and also the peer-to-peer. The client-server model depends entirely on devices called servers, and servers are computers dedicated to providing specific types of services or data, right? So email, maybe you have a web server too. We'll detail different types of servers in just a second. Anyway, a client like your computer or like your cell phone is going to use special software to ask a server for data or those services. It's going to say, hey, can you please send me an HTML file? I would really enjoy that. And what happens then is the server provides the data or service to the client. And so this is really commonly used. You're probably using it right now, maybe to watch this video. Crazy, right? Let's talk about different types of servers, speaking of watching videos. You got file servers, print servers, database servers, network controllers. They control accounts that are on a domain. So like if you have, if you're working for a school district, or if you happen to be working for a company like Microsoft, there's a domain that you probably have an email address for. That means you have a user account, and network controllers are used to manage that data, that information. Also messaging servers, web servers, which are used to access HTML documents, and then also something called CTI-based servers. That's for telephone and computer systems, right? So if you have voice over IP, you're going to be probably using a CTI-based server. A couple of different operating systems here too. Like if you have a client, your client operating systems are going to be different from the types of operating systems that are used by servers. Just note the different tables there, or sorry, note the table there and the different operating systems that are used by a client and then by a server. These operating systems provide slightly different functionality, and so they serve different purposes, clearly, because clients and servers also do. All right, so a peer-to-peer model is different because it doesn't have a server. Peers are just client computers, and they all have equal capabilities and responsibilities. So each has the ability to send and receive data, or to serve and request data. And you know, it's also fairly common. We have Skype and voice over IP, like I just mentioned. and also cloud computing use the P2P model. You also may find file sharing networks like Napster, if you're old enough to remember that. I think Napster is still around, but in a very different form. You have Gnutella and then also G2. So peer-to-peer model is a little different. Each computer accesses data and requests data from its peers and not from a server. So those are two different models that you'll see in your journey through networking. All right, so just a quick recap here. 1.5, understand network topologies and access methods. We talked about different network topologies. We talked about the CSMA CD Ethernet standard and just the Ethernet standard in general. And we also talked about peer-to-peer and client-server models. So thank you so much for joining me for this module. I really look forward to seeing you next in Module 3. Hi, I'm Cullen, and welcome back to Module 4 of Networking Fundamentals. Let's go ahead and check out our agenda and get started here. Just a couple of quick things to go over in this module. We're going to focus on Objective 2.3, understanding media types. We're going to talk about twisted pair cables and also fiber optic cables. So the cables that connect devices all around the globe and that help make up the internet. All right, so wired networks. They're really important. And as wireless connections, like as easily accessible and as widely used as they are, we still depend on wired networks to send our data. Because even if we're using our phone, that phone's connecting to a wireless access point, and that wireless access point is probably connected by a wire to a switch. The most common type of wire used throughout networking is made of copper. It's called a twisted pair cable. And the cable that we rely to send our data super long distances at ultra fast speed is made of glass fiber. And that fiber transmits data via light. And we'll touch on that a little bit more here in just a few moments. But first, let's focus on twisted pair cables. So twisted pair cables, once again, they're very commonly found, the most common, in fact. And the reason being is that they're cheap. They're pretty fast, and they're really efficient at sending data via electrical pulses. We got multiple types of twisted pair cables are available, and they can be installed temporarily or permanently. So if you take a look here down on the bottom right of the screen, we have a patch panel there, right? You have a port being terminated up here in the top right screen. Those are two permanent installations of twisted pair cables. And here you have something called a patch cable, which we typically refer to as an Ethernet cable. All right, part 2 of our twisted pair journey. Each twisted pair cable has 8 wires, and those wires are grouped into 4 pairs. Notice here we have a brown pair, we have a green pair, a blue pair, and then an orange pair. Notice that within each pair you have one that's solid, and then you also have one that is, I guess you would call it striped, right? It's white with an orange stripe in this case for this specific example, but that's the case for every single pair. Each pair is twisted, that's where the twisted and twisted pair comes from, in order to reduce something called crosstalk and interference. We'll detail what crosstalk and interference are in a little bit, okay? So don't worry about that right now. But then we surround all those twisted pair cables with a plastic jacket. That's typically what gives it that quintessential blue look that you see on a standard Ethernet cable, okay? All right, so patch cables. These are the cables that we use to connect one device to another, or one device to an RJ45 port. Each end of a patch cable is terminated with an RJ45 plug using a cabling standard. Okay, we're going to detail these cabling standards in just a moment as well. There are 2 different types of patch cables that we're going to briefly talk about, and they're called straight through cable and also a crossover cable. All right, so these cabling standards that we're about to touch on, they're developed by TIA-EIA, right? The Telecommunications Industry Association and the Electronics Industries Alliance. When making a patch cable, the twisted pair cables are placed in order, and that's part of the standard, right? The order is defined. We then use this device right here to do something called crimping. That's a crimper, by the way, in order to secure our wires into an RJ45 connector. Okay. Note here that that's placed down, trying to secure the cables into the connector. All right, so let's detail some of these cabling standards. You've got an older version, BOGB. Then we have the two that are most commonly used. We have 568A and then 568B. Notice here we've got got two models up on the screen for you. 568A follows a very specific pattern where you have the white and green, then white and orange, then solid blue, then white and blue, and then solid orange, and then the white and brown, and then brown. And then B is a little bit different here, okay? What you're gonna see is that the blue cables are in the same position, and then the brown cables are in the same position, right? So the blue occupy pin, sorry, I actually should probably just go ahead and show you over here on the chart here. The blue occupy 4 and 5, and the brown always occupy 7 and 8. The only thing that's different here is that the orange and green are swapped between a 568A and a 568B. All right, so we use straight-through cables to connect PCs or the devices that we use every day to central connecting devices. The straight-through cable, it's the most common type of patch cable, and it's called straight-through because we use the same standard, right? The wires on each end are organized using 568B, both ends are, or they would both be organized using 568A. In contrast, a crossover cable is called a crossover because of the fact that if you start one end with the 568A standard, it crosses over on the other end to the 568B standard. So let's say that this PC1 here, and then we have PC2. Let's say that this Ethernet cable is terminated with the 568A standard, and then PC2 is connected and is terminated with the B standard. Okay, we would use crossover cables to connect two like devices, like a computer to a computer. All right, so let's go ahead and move on back to the slideshow. Limitations of twisted pair cabling. As we mentioned before, there may be some interference with twisted pair cables, and so they actually can only run about 100 meters, which is just a little over 300 feet, before they start suffering from something called attenuation. And attenuation is just simply the difference between the amount of information that's being transmitted and the amount of information that actually reaches its destination. Okay. And so what attenuation is basically you're saying signal loss, right? So we're losing data due to attenuation. Twisted pair cabling, also susceptible to interference, like I just mentioned. And note that there are 4 different categories of twisted pair cables too. Probably should have isolated these on their own slide, but my apologies. You can definitely download these slides and do that on your own. Note though that Category 3 came before 5, 5 before 5E, and then 5E before 6, right? So notice how the maximum speed rates, the data transfer rates or bit rates, are increasing with each new category. Okay. All right, so we just talked about interference a little bit ago, and what is interference? All that it is just anything that can disrupt or modify a signal, and that ultimately would result in the corruption of data. There are a couple different types of interference. You have electromagnetic interference, you have radio frequency interference, and then crosstalk. Whoops. Electromagnetic interference can be given off by a microwave or anything that transmits an electromagnetic field. And what that can do is it can essentially just throw off those electrical signals that are being transmitted along a wire. Similarly, with radio frequency interference, radio frequencies can interfere with wireless communications. And so it may not impact the use of twisted pair cabling as much as EMI would, but it's definitely something that you should be aware of. And finally, you have crosstalk. And crosstalk actually occurs within an Ethernet cable. And so if you're sending data on one twisted pair and receiving data on another twisted pair, there may be some crosstalk that occurs where the electrical signals on one copper cable start to get mixed with the electrical signals on another one. And so that's crosstalk, and it can definitely lead to data corruption and attenuation. So, all right, let's keep on moving. To combat crosstalk, we actually can shield the twisted pair cables. And so not just crosstalk, but also just general interference can be addressed through the use of shielded twisted pair, or STP cables. All that we do is we wrap each pair with an aluminum shield, and then we put all of our pairs back inside of a plastic jacket. Keep in mind, shielded twisted pair, typically a little bit more expensive than unshielded twisted pair. We also have a certain type of cable that's called plenum rated, and these types of cables are installed inside of walls or above drop ceilings, like you might find in a school, where they can't be hurt by sprinkler systems or any other cabling that, or I guess any other systems that you might have, like lighting systems, things of that nature, electrical systems. And so plenum rated cabling is important because if there's a fire, these cables have a Teflon coating that makes them, that protects them, right? They don't give off high amounts of smoke. Okay, they're used in these situations because standard twisted pair cables have a PVC jacket, which can actually emit a really deadly gas, which makes it really, really dangerous in a fire situation. So you definitely would want to use plenum rated for anything that happens to be near electrical work, happens to be hidden away in the ceilings, or embedded within a building's infrastructure, because you certainly wouldn't want to cause any more hazards than might have already occurred if there was a fire. So keep that in mind. All right, fiber optic cables, right? The last part of our cabling journey here. Fiber optic cables transmit data using light instead of electricity. We commonly just call them fiber. They're actually made of glass or plastic, right? That's what makes the fibers, is glass or plastic. They have incredibly higher data transfer rates. And they're used in a situation when high data transfer rates are required, and also when data needs to be transferred longer distances. And that's because data can travel at the speed of light, which is really fast. You've probably heard that, the speed of light. Also longer distances, light can travel a much longer distance than electricity can before the signal degrades. And so that's why it works so well. It also happens to be a little bit or a lot more expensive in some instances. All right, so there are a couple different modes with fiber optic cabling, and this can be a little confusing, so do make sure that you're paying close attention right now. There's single mode, and it actually just carries data through a single ray of light, and light in this instance is created by a laser. It's used for much, much longer distances, like 10 kilometers up to 80 kilometers, which is really, really far. This is the type of fiber optic cabling that's used to send data across oceans, right? Just mind-boggling. Multi-mode is a larger fiber, so there's a larger fiber density, and that actually carries multiple rays of light. And the way that this happens is that LEDs are used in order to beam light at different angles in order to transfer the speed. So I can't really do it with my two fingers here, so I apologize. But what happens is the light bounces off of one side of the fiber up to the next, and it never actually hits the different light beams. They just go ahead and they intersect, and they're typically different colors of light as well. And this allows you to send multiple data streams on the same fiber. Super interesting as far as I'm concerned. But another quick thing, if you want to point back to the screen here, is that we use multi-mode fiber for shorter runs, right? So it's just 600 meters, which is still a lot longer than any of your typical twisted pair cables, but it's something to be well aware of. Note that there are multiple fiber optic connector types. This isn't necessarily something that you're going to be tested on, but I honestly would strongly recommend that you go ahead and do a quick Bing search and take a look at the images for each of these connector types. Very fascinating stuff, how you build fiber optic cables. Finally, we do have a ton of different fiber optic cabling standards that are available. Definitely want to go ahead and take some time to review this chart. You don't need to memorize it, but do look for trends, okay? Definitely take time to look for trends. Make sure that you know and understand simple things like the specific cabling standard you want to use for the longest transfer distance, and also be aware of I guess what you would say the fastest transfer rate too. Look for things like that, and also look for the slower ones too. All right, so thanks so much for joining me, ladies and gentlemen. We'll do a quick recap here of Objective 2.3. We talked about twisted pair cablings, unshielded twisted pair and shielded twisted pair. We also touched on plenum rated cables as well. And then we just briefly glossed over fiber optic cabling and a couple of different fascinating aspects about it and how it's able to send data really far speeds at really fast rates. Thanks so much for joining me. I look forward to seeing you in the next module. Bye. Hi, I'm Cullen. Welcome back to Networking Fundamentals. We're going to get started right now with Module 5 and continue our journey through understanding wired and wireless networks. Let's go ahead and get started. Let's take a look at the agenda on screen here. Like I said, we're going to cover Objective 1.4, understand wireless networking. And so that means that we've got to understand wireless devices and wireless standards. All right, so let's talk about wireless networks. For a wireless network to work, all devices have to be connected through a wireless network adapter. And so it's a little bit different from the wired one that you guys saw a picture of earlier in one of our modules. I think it might have been Module 2. I can't recall. Don't hold it against me. And so those devices, they connect through radio signals to a wireless access point. That wireless access point, of course, is an essential connecting device that's capable of sending and receiving data with radio signals as well. And those access points still use Ethernet cables, right? They're connected to the internet, for instance, by Ethernet cables, copper cabling still. Okay. So let's talk a little bit more about wireless network adapters. They enable connectivity between any device and a wireless access point, and they work simply by translating bits into radio signals. And if you actually just take a look at my hands here, all that happens is that radio signals, they modulate, so they sort of go up and down, and that's how they represent zeros and ones. A little different from the way that you represent zeros and ones in binary data with electricity or with light. So anyway, back to the screen. Wireless network adapters, they take a lot of different forms. Most laptops now have internal adapter cards, but there are still, and onboard wireless adapters too, which means that it just goes on your motherboard or your MOBO, as tech geeks might call it. But there are still external adapter cards and also USB adapters that allow you to connect wirelessly. Wireless access points, they can come in many forms as well. Oftentimes they're located in our home routers, our SOHO routers at our home office or small office. And, wireless access points, like I had mentioned previously, I hate to hammer this down, but they're connected to switches. Right, and we do have dedicated ones that are specifically for the purpose of sending and receiving data in large organizations. They might be hiding in a ceiling somewhere above you right now, depending on where you're watching this video. But wireless access points, they simply do that same thing. They translate bits into radio signals, and then they send or receive it. And they do a good job of receiving them and then translating them into the electrical signals that are required to transmit data to a switch or to a router. Another technology that we haven't talked about is a wireless repeater. wireless networks are limited in how far a wireless signal can transmit. So if you think about the range of your wireless access point, it only goes so far. You could actually place a wireless repeater here at the end of a network in order to extend the signal range of a wireless access point. Repeaters do this by reading the signal coming from the wireless access point, and then they go ahead and they repeat it and send it out. And of course, we got to make sure our data finds the device there, right? And similarly, it just reverses that process in order to make sure that your device, if connecting to a repeater, is able to send data back onto the local area network and onto the internet, hopefully, right? We'll detail a little bit more about what the internet actually is a little bit later too. Next, bridges. Bridges function a very similar way to repeaters. Bridges sit in between two different wireless local area networks, though. And what they do, just like bridges in real life that connect, two different sides of a ridge or maybe a gully or something along those lines, is they bridge those two networks together and connect them together. This is known as bridge mode. Okay, it's I sort of find it funny every time that I use these semantic words, because sometimes there's just not a better way to describe it than saying like, oh, it bridges things. And as a teacher, I feel like I should get on my own case about using a word to define itself, but this is definitely what it does in this instance. All right, so let's talk about wireless standards. For wireless networks to function, all of the devices, all of the wireless adapters have to use the same wireless networking standards. There are a number of different networking standards that define wireless communications. They're commonly referenced as Wi-Fi, right? Those are the standards, the body of standards that dictate the data transfer rate, connection frequency, and more of wireless communications. The standard, however, is commonly referred to as 802.11, all right? So let's take a look at this chart over here on the right. This is something that's almost, I've taken this exam a couple different times, and I've seen content from this particular chart multiple times. It's really important. A little odd fact, just so you know, is 802.11b was the first wireless standard created. It was the first to market, rather. Shortly after followed A. And what I want you guys to notice is that these two are the key to really understanding this whole table. B came first, so its data rate was what I say slow, and its frequency was low. Okay. A came along, and it was fast, and its frequency was high. I sort of think about the way that alleles in biology work, and I think about the fact that when you create a new technology, it sort of inherits different features from previous technologies. And so I like to think of G as sort of being a child of A and B. And so if we go back to the screen here, you'll see I always think of G as inheriting 54 megabytes per second, or not megabytes, megabits per second from A, whereas it inherits 2.4 from B. So while B is slow and low, A is fast and high, and so G is fast and low. And so if A and B were parents, right, they would pass along those traits to G. And of course, that same type of analogy doesn't necessarily work that well with N down here, but N just gets way faster with 600 megabits per second. And then of course, it uses both frequencies. It uses 5 gigahertz or 2.4 gigahertz as a frequency. So I don't know, hopefully that little analogy helped you remember the difference between those standards. Definitely something that you're gonna see on an exam. Okay. All right, 802.11n. This is the standard that's commonly used right now. There's actually one that's newer than that. I believe it's 802.11ac. But it's a standard because it's fast, right? And there are also a couple of other factors too. It supports multiple antennas. So if you have a wireless router at home, simultaneous connections and data streams can flow into that wireless router. There's also something called frame aggregation that it supports, which is just sending 2 or more frames in one transmission, so the same radio signals, which can double your bit rate. There's also something called channel bonding. So channels we're not going to detail here. It's a little bit beyond the scope of this course, if I recall correctly, or rather beyond the scope of the exam. But you don't want your channels sitting right next to each other because that can cause some problems when you transfer data. But if you're using 2 channels in combination with each other, then you're able to send twice as much data as possible, and it's really quite a positive thing for wireless communication. So one of the things that's not often talked about with wireless communication, at least in general conversations, is that though it's convenient, it's not always secure. And that's because the data is just traveling wirelessly through the air, right? The radio signals just travel unbeknownst to us. And that means that anybody can try to access that data, right? Like it's publicly actually available out there if you have the proper technologies. And so we have to protect our wireless communications. And we do that using wireless encryption protocols. All right, so that's all we got for this module. Hope you join us next time. We'll do a quick recap here. We just talked about wireless devices, wireless standards, and also how to secure wireless networks and the technologies that are involved there. So I hope you had as much fun as I did. Thanks again for your time, and I'll see you next module. Hi, I'm Cullen. Welcome back to Module 6 of Networking Fundamentals. We're going to get started here with understanding Internet Protocol, or IP, as everybody likes to call it. All right, let's go and take a quick look at our agenda. We're going to go ahead and cover 2 objectives today. First one, 3.2, understand IPv4. Within that, we're going to detail IP version 4 or IPv4. We're going to talk about the address categories for the protocol, talk about network address translation, and then move on to discuss default gateways and DNS servers, and then finally touch on subnetting and CIDR. Then lastly, we'll go ahead and touch on IPv6 as well as a protocol, the ultimate replacement or the eventual replacement for IPv4. Okay. The Internet Protocol resides on the network layer. Go ahead and recall that from our detailing of the OSI model. IP addresses are used to help devices send and receive data across networks. Remember that they are very much like our mailing addresses. So if you mail something to your mom, or you mail something to a friend, same way computers communicate. They use addresses in order to make sure that information goes to its intended destination. IPv4 currently is the most commonly used communication protocol, but IPv6 is starting to replace it, and it's already being used more widely everywhere. Okay. All right, so let's talk a little bit more about IPv4. So this is the 4th version. That's why it says V4. It's the first version, though, of the IP protocol to be widely used. IP addresses consist of 4 octets. All right, so we have 4 octets, and we touched on this briefly in a previous presentation, but super important to know, okay? So you got 1, 2, 3, 4. We have 4 different examples here. Each has 4 octets. Each octet is separated by a decimal point. You may refer to it as a period, but call it a decimal for this sake. Each octet represents 1 byte, or 8 bits, meaning that an IPv4 address features 32 bits. So what that also means is that we can convert those decimal values into binary. So let's take a look at a simple octet here. Let's say 192 as an example, okay? We'll go back to this chart. If I take a look at the number 192 as an octet, and I say, hey, I want to convert this into binary. What I can do, if you take a look at this chart here, is if if 128 as a value fits into 92, then I can go ahead and I can put a 1 here and say yes, I can in fact subtract 128 from 92. So if I do that, do some math, probably wishing I was using a calculator right now, aren't you? What we end up getting is 64. Well, so now my leftovers, 64. Can I subtract 64 from 64? The answer is yes. So I'm going to go ahead and I'm going to put a 1 right here. And if I do that, 64 minus 64, all of a sudden I have 0 left. You might be bummed out that you have 0 left, but it's okay because it actually makes the rest of our job very, very easy. I'm going to say, hey, can I fit 32? Or rather, can I subtract 32 from 0? Well, no, there's nothing there remaining, so all of a sudden I put 0. The answer is no, and that's what 0 represents, is no, or false. Same thing with 16. I've got a 0 there. There's nothing remaining, so I can't even subtract 8, or 4, or 2, or 1. And so, of course, my decimal equivalent for this would be 192. And if you take a look at the examples up above, say for 224, we did the same thing here as well. So you see, we can subtract 128 from 224, and then whatever's left over, we can subtract 64 from that. And then, of course, we would only have 32 left over if we did that, which means that we put a 1 here, and then the rest are all zeros. And that's how we would translate decimal into binary, and also vice versa, how we can take binary and translate it into decimal, okay? All right. Next, there are also static and dynamic IP addresses. So IP addresses can be assigned statically, which means that they're manually assigned to a host, and so they don't change. That's what static means that it doesn't change. Dynamic, in contrast, means that it does change. And so with these types of addresses, we automatically obtain them from a server, which is pretty darn cool. So, if you're moving from location to location, you're probably having IP addresses assigned to you automatically, and you may not even be aware of it. This is something that completely just, gave me a headache, made my head spin when I was first learning about this stuff. So, all right. There's another reserved range for, or another reserved network, right, for it's in Class B. It's called Automatic Private IP Addressing, or APIPA, right? If a client can't get an IP address from something called a DHCP server, which is Dynamic Host Control Protocol server, and an IP address hasn't been configured statically, then it auto-assigns this number to itself on the network. So it'll have an address within the 169 range. This is useful because if your computer can't access the internet, or there's something wrong and you can't automatically obtain an IP address, then you're going to self-assign an APIPA address, and then that'll allow you to communicate with all the other devices that are on your local network. All right. Network address translation. Let's go ahead and move on and talk about how public and private addresses really function and how they work out in the open, out in the wild, if you will, right? Network address translation is just simply the process of modifying IP addresses while in transit across a traffic routing device. So what happens here is that this, let's see here. So we might have computer 1 sends information to a switch. The switch goes ahead and sends it off to the router. And then what happens is that packet might have the addressing information of 192.168.0.255. And what's going to happen is that there is, and this is my translation process here, right? That router is going to go to work and it's going to translate this address into this one. It actually knows exactly what that address is, so the process isn't as messy as that, but I just thought it'd be more fun if I scribbled on the screen. And so everybody that's out on the internet, right, this cloud here, they're going to see this public-facing address. They're never going to see the private address that's being used by the computer on the local area network. And this is a really cool process because what it does is it makes it a little bit easier for us to use IPv4 addresses. I guess I should have said that IPv4 addresses are limited. We actually have more devices than available addresses with IPv4, which is a huge problem. And so this allows us to make better, more efficient, more effective use of them. So, all right. And of course, here's a little bit more information on NAT, right? Stuff I just said. It was developed to provide a temporary solution to the shortage of IPv4 addresses. So, okay, so let's talk about default gateways and DNS servers. For a device to be able to access the internet, if you're on your computer right now, it has to have a default gateway. And you also probably will need a DNS server unless you are really good at remembering and recalling IP addresses. Default gateways provide default routes for TCP and IP hosts, right? Our computers, our devices, to use when communicating with hosts across the internet. So anytime you send a text message, this process, default gateway is probably being used. The first IP address of the device that a client computer will look for is actually the address that belongs to the default gateway. And so this network address we were talking about, the first address in a network range or on a network, is going to be assigned to a router. All right, that router is and it does serve as the default gateway. So keep that in mind. Here's a little data going through the router and then of course onto the internet. It's pretty exciting stuff, this data transfer. Let's talk about the domain name system, okay? If let's say we want to go to Bing, okay? So I'm on the laptop and I want to go to www.bing.com. Well, that server that's located over here on the top right, that has all of the good Bing HTML files and all the other code that we need in order to create the Bing.com web page on our screen. And so what we need, though, is we need something to take that name and translate it into an IP address so that we can access the Bing server, because it's not called Bing.com. The server actually has an IP address. And so let me actually erase the ink because I think my animation is going to cause me troubles and make me back up with what I just said here. But let's now pretend that that's not the Bing server, but it's actually a domain name system server, okay, a DNS server, all right? And so what's going to happen is we're going to type in bing.com into our browser, and then that information is going to be relayed to the DNS server. And then what happens is that DNS server is going to send us back the IP address for bing.com. That's the actual IP address for Bing. And if you type that into your browser right now, you actually should be able to access Bing without typing in the name. But what it's going to do, what that DNS server did, was it translated that name into an IP address that we can then use to access the web server where Bing is located. Internet Protocol version 6 is just a new generation of IP addressing. It solves a lot of the limitations with IPv4. The difference between the two is that IPv6 is 128 bits, while IPv4 is 32 bits. And so IPv4 is approximately just 4.3 billion IP addresses. All right, that's the result of 32 bits, whereas 128 bits results in 340 undecillion addresses. And if I wrote out all the zeros in an undecillion, let alone 340 undecillion, I'd be writing for a really long time. I encourage you to look up how many zeros that is. It's pretty cool. And in fact, it's enough addresses to give an address to every single grain of sand on Earth right now. And that is just mind-boggling, absolutely mind-boggling. I had a student tell me once, they did some calculations. They said that not only is it enough for every cell in every human body in the world,
to have an IP address, but each individual on the planet could also have 500 extra addresses for all, or 5,000 extra addresses for all their devices. I might have messed that up, but I thought that was a pretty cool statistic.